Hello everyone, I'm Varun and I'll be talking about single photon structured light. Structured light 3D imaging has inherent trade-offs balancing acquisition time, precision of scan, and robustness to high noise regimes. For instance, certain structured light techniques achieve high depth resolution by projecting multiple patterns but require long acquisition times. At the other extreme, some techniques project a single pattern, facilitating high speed, but result in loss of detail. Presented here are some challenging low SNR regimes that exacerbate the trade-offs in structured light. These include dark objects, strong ambient illumination, and highly dynamic scenes. In this work, we introduce a novel structured light system based on single-photon avalanche diodes or SPADs. A SPAD pixel functions like a photon teaspoon that can detect the arrival of individual photons. If more than one photon arrives during an exposure window, irrespective of the number of photons, the returned value is 1 and 0 otherwise. Since photon arrivals are stochastic, these pixel values are binary random variables. So what do SPAD images look like? Each image is binary with a greater frequency of ones in bright regions and lesser in dark regions. The predominant source of noise is the random arrival of photons, also called photon noise. Since the SPAD directly detects photon arrival, there is negligible read noise involved. An additional benefit, which we exploit, is the high frame rate of SPAD devices. Single-Photon SL consists of a SPAD camera and a DMD-based projector operated at extremely high speeds. Our key observation is that binary frames are sufficient for a large family of binary structured light techniques. We design novel coding schemes that offer robustness to photon noise based on a combination of gray codes and parity patterns. However, many of these parity patterns, due to their high spatial frequency, are strongly distorted by imaging phenomena such as projector defocus. For this reason, we design a new class of hierarchical codes using error correction and binary shifting that provides robustness to various non-idealities. We now present 3D reconstruction results using single-photon structured light. Our prototype uses the SWISS-PAD2 array, a 512 x 256 pixel sensor. We also use the DLP6500 DMD, which can be operated at 20,000 Hz and a resolution of 1024 x 768 pixels. For simplicity, we run this SPAD array at the same speed as the DMD-based projector. We first demonstrate the high precision of single-photon SL on a static scene. We show a series of projected patterns and their corresponding frames. One way to improve the robustness of conventional codes to photon noise is to simply repeat them. Unfortunately, this does not achieve good performance. In contrast, given the same acquisition time and illumination power, our proposed coding scheme provides considerably better results. We now demonstrate the capabilities of single-photon SL on low albedo scenes. The reference image shows an inverted V-groove covered by Acktar metal velvet, a material which returns just 0.1% of incident light. Evidently, much fewer photons are detected when a bright pattern is projected. Despite this, our proposed coding scheme can obtain an accurate 3D reconstruction. Here is an example of a commonplace dark object, a car tire. The tread patterns are clearly visible. Next, we demonstrate the capabilities of single-photon SL on highly dynamic scenes. Here is a white cloth rapidly waved in front of the camera. Capturing such a non-rigid object requires high-speed acquisition. Otherwise, excessive motion blur is induced. As the depth video demonstrates, single-photon SL can recover detailed 3D geometry of non-rigid objects. We also include mesh reconstructions of a few timestamps to clearly show the deforming folds of the cloth. Here's another scene with extremely fast motion, a jack-in-the-box toy which springs up in less than 40 milliseconds. A conventional depth sensor, such as the Kinect, operates at 30 fps and is too slow to recover depth at intermediate instance. However, single-photon SL can run at a significantly faster 2000 fps and recovers fine details of the toy as it springs up, such as its ears. In summary, single-photon SL is designed to address various trade-offs inherent to structured light systems. Single-photon SL can enable extreme 3D imaging that features high speed, high precision, and robustness in low SNR conditions.